So Vivek from Georgia Tech will give the next talk, and he's going to talk about concrete type inference for code optimization using machine learning with SMT solving.
Good. Okay, I think we're good.
Yep, stage is yours.
Okay, thank you. Yeah, it's a pleasure to present this work from our group, and it's unfortunate that the lead PhD student, Fangke, could not be here. So let's step back and look at the broad space of application developers. And what we see in today's era, especially as we approach the end of Moore's law, is that carrying a lot of the burden are ninja programmers who are hardware experts. And they code in C, in CUDA, in assembly, hardware intrinsics for all the new kind of accelerators coming out. And above them, we have experts in developing libraries and frameworks who might code in C++, Rust, SYCL, and so on. And then we have a vast number of domain experts who write in languages like Python, MATLAB, JavaScript. And what we've seen over the last decade is that Python has emerged as a dominant programming model for domain experts. And here are a number of frameworks that you might recognize that are all Python-based. Machine learning frameworks, NumPy, SciPy, Pandas, and so on. So let's look a bit at the needs of the domain experts from the perspective of both productivity and performance. So productivity is an absolute must for them. They're not down there at the ninja level or even at the library framework developer level. They benefit a lot from Python's dynamic typing, interactive programming, the fact that you have many high-level aggregate operations, rich libraries, and also the fact, quite frankly, that over the last couple of decades, Python is the introductory language offered in most CS1 classes. So they've got productivity, but they want performance without compromising productivity. They can get performance from high-performance libraries, but that's only if the computation they want to perform matches an existing library. If they have some code that does not match a library, then they are reliant on optimizing compilers. There are JIT compilers for Python, and there are also some ahead-of-time compilers. So the focus of this paper is really to start with on ahead-of-time compilation, and certainly in this case, you need concrete types to deliver performance. And to give you a feeling for what the concrete types might look like in a couple of cases, suppose you have a sample Python function, f of x, y, x comma y, x and y are two parameters. It has an operation like x plus equals y. In the research compiler that was developed in our group called Intrepydd, that was presented 3 years ago in Onward 2020, you could specify types using type hints. And as shown over here, f1 is a variant of the function where x is a one-dimensional array of int32 and y is a one-dimensional array of int32. f2 is another variant where x is a two-dimensional array of int64 and y is a 1D array of int64. And that's also conformable with x plus equals y. And in the Numba AOT module, you can use decorators as shown over here. And I don't have time to get into it, but past work has shown that if these types are provided, you can get very significant performance improvements. At the very end, I'll give you some indication of what that looks like for some benchmarks. But keep in mind that code optimizations for these languages can do a redundancy elimination wholesale on large aggregate operations. So there's a lot more benefit from code optimization than might occur from LLVM-IR, for example. Okay, so our goal is to somehow add concrete types so that we can help the domain experts obtain the performance they need. So how do we do this? Well, one is we can ask the programmers to provide it, but that's counter to our productivity goals. There has been past work in our community on using machine learning. And there are some limitations. Actually, frankly, we were looking for existing solutions to just move forward on our optimization research. And what we found is if we directly use some of the past work on machine learning, we get reasonable accuracy on a per variable prediction, but we get combinations that are inconsistent. And then there was also past work on combining ML with rules-based analysis. In our opinion, that was more focused on software engineering than code optimization, and often provided like a single type, which might be an abstract type with like any or something like that, which is not amenable to the concrete types needed for code optimization. There's been past work on solvers, particularly SMT solvers and other constraint solvers. The good thing about this work is that all the combinations they predict will be type consistent, will type check, but if you encoded the constraints correctly. But there can be a large number of these type combinations, and the SMT solver has no clue as to which combinations are more likely. So our approach is to explore how both of these can be combined. So we want to statically generate a manageable set of type assignments that are both likely and concrete type assignments that are both likely and consistent for some regions of code in a Python program. We'll focus on functions, but this could apply to any code region. And we are fine with getting multiple concrete type assignments because we know how to do this in the PL community. We can generate multiple versions and dispatch to the appropriate version at runtime. So to give you a feel for the ML models, we actually evaluated 4 in the paper just to get a sense to what extent the model had an impact on accuracy and overall results. So these are some of the results just for predicting the type of a single variable. And you can see 4 models. The first is more a statistical model, just frequency-based. The second and third are extensions from past work. And earlier this year, we had the opportunity to experiment with GPT-4, the API also as a model. And the paper has the details, and we see there's a bigger difference across models, and this is for top 1, top 5, top 10, top 20, when you have a lower K for top K. But overall, GPT-4, which we of course did not train, and I should mention the training set used for the other models was different from these benchmarks, did perform the best. Okay, so this figure in the paper gives an idea of what you can do on the left side of the figure if you only went with ML type predictions. You do get likely types, which is great, but when you start looking at combinations of type of variables, you may get many invalid combinations for the x plus equals y example. For example, a case where y is a 2D array and x is a 1D array. You can think of it as a minor kind of hallucination, but it comes about by just combining types from different variables. So this is a major issue. All those examples shown in red are examples of types that are predicted but are inconsistent. And in fact, table 4 in the paper looks at it more quantitatively. The number of types in some of the benchmarks can be really huge, 10 to the 10, even as high as 10 to the 65. And only a small fraction of them are consistent. And on top of that, there are cases when there's still zeros, where none of the ML predictions from these large numbers end up matching the ground truth. So that's a challenge if you just use ML. So what if you explore using a type solver, an SMT solver, and in our case we use CVC5. So the type system at the bottom, which is also in figure 1 of the paper, shows the type space that we're exploring for this work. And there can be constraints. For example, the fact that the key type for a heap data structure needs to be scalar. So you can see some constraints related to that, or conformable ranks for certain operators, and so on. And there's also, to make things tractable, we can put a bound on the rank of an array that we want to consider. Here we're showing constraints where the array rank is less than or equal to 3. Of course, it could be replaced by some other constant. And also some constraints that allow for enforcing uniform bit widths in certain operations. And the table shows that if we just let the SMT solver predict the plausible types, we will get a large number. That's a TC column. But if we add the finite type space constraints, we reduce it a bit. And if we add uniform bit width, we still reduce the space. But there's still some cases where it's very large. So this was the right-hand side of this figure, where the nice thing is all the predictions are type consistent, but there's a large number of them, and we don't know which ones are going to be more likely. So the first attempt at trying to combine the two was saying, okay, let's take the type predictions, the top K predictions from ML, and add them as constraints in the SMT solver. If you have top 5 for a variable, you have 5 types. Add to the SMT solver that the type of the variable could be the first type, second type, or the second type, or the third type, and so on. That's a good start, but what we found is that it was too much of a hard constraint. In some cases, it would still miss one type in the ground truth, and then the Cartesian product would mean that you have 0 type combinations that match, or in some cases, there would still be too many solutions. And the issue over here is when you look at top K, you want to simultaneously consider multiple K values for different variables. So now the paper has the detail on a scoring function that we use. And the idea over here is if you have 2 predictions, for example, one where variable X is in the top 1, variable Y is in the top 1, and variable Z is in the top 10, we give it a score depending on how often it appears in top 1, 5, 10, or 20. And if in case 2, a type prediction, X is in top 1, you have a top 1 type prediction. For Y, you have a top 5. For Z, you have a top 5. You add it up, and then you do a lexicographic comparison that prefers more occurrences in top 1 than in top 5 and top 10. And then what you do is you essentially add to the SMT solver a constraint that the score should be greater than equal to a threshold. And this is a softer constraint. It can even accommodate some types that were ignored or not predicted by the ML system. So with the refined approach, and there are a lot of details in the paper, with the refined approach, we find that we are down to a manageable number of types. And in the GPT-4 case, we can see that the numbers vary from the variance from 2 to 186. And it turns out that 186 is totally manageable. The results will show you actually generated 186 version. For one benchmark, IPNSW, we did not happen to get a type that was in the ground truth, so we're going to fall back to the default Python version in that case. Which brings me to the performance results that are in the paper. What we see over here is that there are 10 benchmarks, one for each row. There are columns per ML model, and within that, there's a performance improvement relative to the original Python code when our types are fed into the Numba AOT model or when they were fed to our Intrepydd C++ code generator. The geometric mean at the bottom shows that as a geometric mean, the improvements range from 16x to 60x. But there were many individual cases where this performance improvement due to code optimization was many hundreds, and in one case, even more than 4,000. So to summarize, we introduced an approach for concrete type inference that enables code optimization for dynamically typed languages without requiring any input from the domain experts. We combine machine learning and SMT in a way that can work effectively, these soft constraints that have this notion of a progressive constraint relaxation, and get a manageable number of predicted types. And we've shown significant performance improvements by using these types. And in fact, looking ahead, we think there's an exciting opportunity to explore these combinations of machine learning and SMT. And certainly that's what we plan to do more of at Georgia Tech. My good friend, we are lucky that my good friend Vijay Ganesh, who's an expert in solvers, moved to Georgia Tech recently. And if anyone here is interested in doing a PhD or a postdoc or a faculty position in this general area, please feel free to get in touch with me. Thank you.
All right, is there any question? Please.
Thank you for the great talk. I have one question. Does the type annotations will affect the functional correctness of the produced programs?
So the question is, the type annotations, I didn't get into the details of the multi-version code generation, but this is a classic technique in PL. So we'll generate all these versions for different types. At runtime, we will dispatch. And so each code is a specialized version of the original function for those concrete types. So it should not change the correctness because it's a specialized implementation of the original code. I don't know if that was your question, though.
Okay. If you do this runtime dispatch, then that should be fine.
Yeah.
So and about the precision on the overall types, did you do experiments to run the experiments on different types? Because, for example, if the integer type int 32 takes 90% of all the types, then the final results may be imbalanced or biased.
Sorry, I didn't. Are you talking about the prediction part or the code generation part?
The prediction part.
So what might be invalid? I didn't get that question.
For example, if the final code, if integer type takes int 32 type takes 90% of all the types in the code, then if I have a model, then I just predict everything as int 32, then my precision would be my accuracy would be 90%, because the imbalanced types in the code. And I think this is very common in practice.
Let's discuss further offline, because the point I was trying to make is you can get good accuracy for predicting a single variable, but it's the type combinations that become challenging. So we can discuss more offline. Yeah.
We can have another quick question.
Thank you, Vivek. Wonderful talk. Could you compare this with, say, profile-guided optimization, where you collect information from one or more runs about what the types actually are that are seen at runtime?
Yeah, thanks, Elliot. So I did not get into the details of some of the training that we did for those two models. And there, the training data set, we actually used the monkey type profiler and collected dynamic types from runs of the program and used that for training. But the results from GPT-4 were quite amazing. And offline, I'm happy to share the prompt and all with any of you that was used to get those predictions. So, yeah.
So we need to move on. I would really encourage you to get in touch with Vivek. Thanks a lot for the talk again.
Thank you.